Hey, guess what, man?
What?
I gave our teacher a chili pepper on Rate My Professor last night, man.
Oh.
Hello, class. Today we will learn about buoyancy forces and how they are used in the world around us. As you may know, some substances are more dense than others. And as you may recall, less dense substances float on top of more dense substances. Now, you may be thinking, wait a second, steel ships are more dense than water. How can steel ships float? Well, that is explained in Archimedes' principle, which states, any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. Therefore, the steel ship floats because it is displacing an amount of water equal to its weight.
Because of this displacement, is there any way to tell how far the ship will sink into the water?
Yes, there is a way to tell where the water line will be on any ship. Let's go back to the example of the cargo ship. As you can see here, part of the ship is underwater. To calculate how much of the hull is underwater, we take the weight of the boat and divide it by the density of the water, 1,000 kilograms per meters cubed. The acceleration due to gravity, 9.81 meters per second squared, and the area of the bottom of the ship.
Boy, get this loaded up pronto.
Aye, aye, sir.
As more crates are added to the ship, it becomes heavier and therefore raises the water line.
Whoa! Where am I?
Anyway, as I was saying, as the ship gets heavier, the water line will rise.
That's all we can carry. Just throw off.
Actually, he could carry more cargo than that. Let's do an experiment to see how much cargo he could carry. On each desk, I have a replica of the cargo ship I used in the illustration. Our goal in this experiment is to find out how much weight the ship can carry before the water line reaches the City Lines logo. Water basins are over on the table. You may begin.
Hello, my name is Andrew Bermudez, and today I will be doing an experiment on buoyancy. First, I must calculate the weight of the ship. According to this mass scale, the ship's mass is 722 grams, which by moving the decimal point over 3 places becomes 0.722 kilograms. Now I must measure the height between the bottom of the ship and the bottom of the City Lines logo on the side, which is 3.3 centimeters. We'll be needing this measurement later. Now I must find the area of the bottom of the hull of the ship. The width across is 14.5 centimeters, and for the length,
because of the area's unique shape, we will be calculating it in various sections. We will first be starting with a rectangle with a length of 28 centimeters. After calculating using base times height, we find that it is 406 centimeters squared. Our next area is a half circle, which we will calculate using 1/2 pi r squared. Using half of the 14.5 centimeter width, we find it to be 82.6 centimeters squared. Our final area is a triangle with the height of 20.5 centimeters. After calculating it using 1/2 base times height, we find that it's 148.6 centimeters squared. We are now going to calculate the total area. Taking the 3 areas, we add them all up to find that the total area is 637.2 centimeters squared. After converting the total area over to meters squared, we find it as 0.0637 meters squared. Also, when converting the height over to meters, we find that it is 0.033 meters. To calculate the total weight, we need to manipulate the equation H equals F over dGA and plug in the numbers to find that the total force is 20.62 newtons. Now, using the equation for weight, we will now take our weight and convert it over to mass. This gives us 2.102 kilograms. In turn, we can then take this and convert it again to 2,102 grams. We now take the total mass and subtract out the boat's mass. This gives us our calculated mass that's needed to put into the ship.
Now that I've calculated that the needed mass is 1,380 grams, I'm now going to experiment to see if that calculation is correct. In each of these tubs, I have 500 grams worth of coins in there. Now I will put on another tub and put coins in there until the water line reaches the logo. The water line has now reached the logo on this side. Now I will calculate the mass of the coins I put in, which is 230 grams.
Now we add up all three masses together to find our experimental mass. We then take this number to calculate the percentage air, which we then find to be 10.9%.
So what have we learned? Today we have learned that the greater weight that a ship applies to the water, the greater buoyant force is needed to keep it afloat.
Hey, wait a second. If, like, Archimedes said there's a buoyant force acting on something, even if it's, like, totally underwater, how come it sinks to the bottom?
For this example, let's take a look at an old sailing vessel, like a pirate ship.
Sir, we have an unknown ship sailing on the horizon. Ready the cannons. Aye, aye, sir. Fire! Aye, we've been hit, Captain. Save the treasure! Save the treasure!
You are right in that there is a buoyancy force acting on this treasure chest. However, the weight is so great, it is able to overcome the buoyancy force and accelerate downward. Also, the treasure inside has a greater density than water, allowing it to sink.
What about the ship? How does it sink?
It's not as difficult to understand as you might think.
Prepare the dinghy! Aye, aye.
The reason why this pirate ship sinks when it gets damaged is because there is now water inside the hull of the ship. This water applies a pressure in addition to the ship's weight from above that outweighs the buoyancy force, causing the ship to sink, even though the wood that makes up the ship is most likely less dense than water. Even though they're submerged, there's a buoyancy force acting on all objects in the water, even a diver.
I hit the jackpot.
Buoyancy force also makes it easier to pick up heavy objects underwater. Well, it looks like class is now over. Remember to do the assigned homework.
Sam, you won't believe the pirate treasure I just found.